everyone, welcome to ICC Possible Walkthrough series brought to you by ZNotes. I'm Yumna. While I'll be your host, we have an amazing contributor, Roshul, who will be guiding you through all the questions in this summer 2023 paper. Together, we'll make sure you're well prepared and confident for your exams. Don't forget to subscribe so you don't miss any episodes. Let's get started and dive into the fascinating world of physics.
Okay, so yeah, today we're going to be doing the summer 2023 paper 4-1, which is theory. So yeah, let's begin. So the first question, it says that it shows a straight section of a river where water is flowing from right to left at a speed of 0.54 meter per second. And a swimmer starts at point P and swims at a constant speed of 0.72 meter per second relative to the water at right angles to the current. So as visually, that would be this arrow 0.72 as the current is moving left to right, and this is perpendicular to the current. So the question asks, determine relative to the riverbank both the magnitude and the direction of the swimmer's velocity. So here we have two ways. So first of all, we have to draw a diagram. So we draw 0.72 a line straight. Either you draw a vector diagram with proper dimensions. So you draw a 7.2 centimeter line straight and then a perpendicular line of 5.4 centimeters leftwards. And then you draw this resultant vector, this one, and you either measure the length of it or using Pythagoras theorem, you calculate the length of this one, which is 0.9 meter per second. So that becomes your magnitude of velocity. Now for direction of velocity, we need to find out this angle. So this angle, there's two ways. Either when you draw the vector diagram, you measure it using a protractor, or you figure it out by using your calculator. Is just tan inverse 0.54 divided by 0.72 as shown here. So you can do this two ways, either using a triangle or using a vector diagram. Next up, this question asks us that after 1.5 minutes, the swimmer reaches point Q. Calculate the distance between P and Q. We all know that distance is equal to speed into time. Here we calculated the speed, which is 0.9 meter per second, into the time is 1.5 minutes, which is 90 seconds. So here the distance is gonna be 81 meters. Yeah. So now next question is, when the swimmer is crossing the river, his actions produce a constant forward force on his body. Explain why he moves at a constant speed. Now for this one, so while the swimmer is putting a constant force forward on his body, as he's swimming in the water, the river produces a resistive force or a drag force against the motion of the swimmer. And this resistive force is equal to the constant force provided by the swimmer. So your net force becomes zero. And since there's no net force, there's no acceleration, because acceleration is equal to force by mass and net force is zero. So since there's no acceleration, it moves at a constant speed. So we can write that resistive force by water. So no net force, no acceleration. Okay, now we move on to question 2. So question 2 shows a motorcyclist accelerating along a straight horizontal track. On the straight horizontal section of the track, the motorcyclist accelerates from rest at 7.2 meter per second square. The motorcycle reaches the end in 5.3 seconds. Calculate the speed. So as you know, v is equal to u plus at. Here initial velocity is 0 since it accelerates from rest. So the speed is just acceleration into time taken, which is simple enough. It is 38.16 meter per second. Now, calculate the resultant force on the motorcyclist and motorcycle on the straight section of the track. Now, as we know, force is equal to ma, which is mass into acceleration. So here the mass is 240 kg, acceleration is 7.2. So the answer is 240 into 7.2 equal to 1728 Newton. Now, part B asks that at the end of the straight section, the track remains horizontal but bends to the right, as we can see here. When the motorcycle reaches the bend, she travels around the bend in a circular path at constant velocity. Well, constant speed. Velocity is a vector quantity. State how a vector quantity differs from a scalar quantity. So as we know, a vector quantity has a specific direction. That's what makes it different from a scalar quantity. It has specific direction. Scalars do not have one. Describe what happens to the velocity of the motorcyclist as she travels around the bend at constant speed. So, as we know, it mentioned in the question that she travels at constant speed. However, as we just talked about, velocity is a vector quantity, so it has a specific direction. So here, as it bends, it changes direction. So that's why her velocity changes. Hence, we can say that her velocity changes. Now, explain why there must be a resultant force on the motorcyclist as she travels around the bend. So, as we discussed in the last question, her velocity changes because her direction changes. So, since there is a change in velocity, this is the symbol for change in velocity, there must be acceleration. As we know, force is equal to mass into acceleration. So, for acceleration, a force must exist. And this force, in this case, acts perpendicular to the motion of the motorcyclist. Since it moves in a circular pattern, and in a circle, the force always acts towards the center of it. So the force would be acting about like this towards the center. So that's why there's a resultant force on the motorcyclist. A rubber balloon is inflated with helium and seals where no helium escapes. It's positioned immediately below the ceiling in the room. Heaters are switched on and the temperature of the room rises. When the heaters are first switched on, the temperature of the air immediately below the ceiling increases faster than the temperature of the air in the rest of the room. Explain why this happens. Now, as we know, hot air is less dense than cold air. So that's why hot air rises up and cold air descends. So since hot air rises up, the air just below the ceiling heats up faster than the air, further below in the room. So that's why, because hot air is less dense and it rises up. Now, the next part asks that the temperature of the helium in the balloon increases as the rubber stretches. The volume occupied, and as the rubber stretches, the volume occupied by the helium increases. State what happens to the motion of the helium particles as temperature increases. Now, we know that as temperature increases, the kinetic energy of particles increases because temperature and kinetic energy are directly proportional. So as the kinetic energy increases, their mass remains constant. Kinetic energy is half mv square. So as a result, their speed increases. Hence, they move faster. Now, as the rubber stretches and the volume of the helium increases, the pressure of the helium remains constant. Explain in terms of the particles of helium how the pressure of the helium remains constant. So now we have a balloon. Now the area of this balloon is expanding. So the particles collide less frequently with the walls of the balloon because they have to now travel a greater distance. So normally in this situation, the pressure should have decreased because less collisions per second, so less force exerted per second. However, it's mentioned that the temperature of the helium increases. So as we discussed in this part, as the temperature increases, the kinetic energy increases and they move faster. So if they move faster and they have more energy, so they also collide with the walls with the greater force. So because of the temperature increase of the balloon, the pressure should increase. So we can write it as due to temp increase, pressure increases. Due to volume increase, pressure decreases. These two changes balance each other out. That's why the pressure is constant. There. Now, we move on to the fourth question, which asks us that a student investigates the efficiency of a filament lamp and it shows the filament lamp with a glass bulb immersed in the water in a beaker. The reading on the thermometer is 19 degrees Celsius. Only the glass of the lamp is in contact with the water, and the electrical connections are completely insulated. The lamp is switched on. At the end of the experiment, the temperature of the water is 21.5 degrees. The mass of the water is 600 grams, and the specific heat capacity is 4200. Show that the increase in internal energy of the water is 6300 joules. So, as we know, E is equal to mc delta T, which is mass into specific heat capacity into change in temperature. So here, as the water supply is being heated, we're measuring from the thermometer. So we know that there's 0.6 kg of water. The units are important because specific heat capacity is given in kg into 4200 joule per kg degree Celsius into the temperature change is 2.5 degrees since it's 21.5 degrees Celsius minus 19. So into 2.5 degree Celsius, which is 6300 joules. As we can see, hence we have shown that the increase in internal energy is 6300 joules. Now, in the experiment, the lamp is switched on for 500 seconds. The power supplied to the filament lamp is 13 watts. The useful energy from the lamp is transferred as light, and the energy that increases the temperature of the water is wasted energy. Determine the maximum possible efficiency of the filament lamp. Now, efficiency is equal to useful energy emitted by energy supplied into 100 as a percentage. So here useful energy emitted, no sorry, so energy supplied here is energy is equal to power into time, which is 13 watts into 500 seconds, which is 6500 joules. So if the total energy supplied is 6500 joules, and as we figured out in the last part that 6300 joules is energy wasted, that means the useful energy is 6500 minus 6300, which is 200 joules by 6500 into 100, which is 3.1%. This is the maximum possible efficiency. Now, the next part asks us that the efficiency of the lamp is less than the value determined in A2. So, just one reason for this. Well, there's many possible reasons for this. Basically, they all deal with the fact that here in this diagram, the heat energy that lamp transfers to the water, it can then transfer to the beaker by conduction, to the surrounding air by radiation, etc. Hence, we can write that some energy also transferred to beaker. Hence, here the energy supplied for that given amount of light will have to be greater than what we measured. So that's why the efficiency falls down, because the like percentage of useful energy supplied as light is less, because even more energy now is supplied as heat and wasted. Now, question 5 shows a block made of glass that has a refractive index of 1.5. The block has one curved side and three straight sides. There are right angles at C and D. The curved side AB is 1/4 of the circumference of a circle with the center at point P. Now, a ray of monochromatic light enters the block through the curved side AB and strikes BC at this point. Some light emerges into the air and some is reflected. State what is meant by monochromatic. As we all know, Monochromatic is light of a single frequency. Nothing complicated here. Next, it asks us explain why the ray of light does not change direction when it enters the block through side AB. So, as we know, when entering through side AB, if we take this as a straight line of the surface it's entering, just a rough tangent, so here it's perpendicular to this tangent. Hence, this line is the normal. Hence, angle of incidence I is equal to 0. And then, therefore, as a result, angle of refraction is also 0. So that's why there's no change in direction, it just moves straight. And as a general rule, we can write that the light enters perpendicular to the surface. Any curved surface, the light will enter perpendicularly. So there is no change in direction. Now, show that the critical angle C for the glass of refractive index 1.5 is 42 degree. As we know, we have the formula n is equal to 1 by sine C, where n is the refractive index and C is the critical angle. So, critical angle is equal to sine inverse of 1 by n, which in this case is 1.5. Hence, sine inverse of 1 by 1.5 is 41.8 degrees or 42 degrees. D. Part D says that the figure shows that the angle between the ray of light and line AP is theta, where line AP is at right angles to to side BC. Angle theta increases to 45 degrees. Staten explains what happens to the light that strikes P. Now, the light that strikes P, this is angle theta as we can see, and according to the question, it's 45 degrees. We have just calculated in the last question that the critical angle of this piece of glass is 42 degrees. So we know that when the angle of incidence is greater than the critical angle, which it is in this case, 45 is greater than 42, then total internal reflection takes place. That is, as we can see in the diagram, the light will basically hit this point P and then all of it will be reflected. Unlike what we can see here, this will not be the case now. Because the angle of incidence is now 45 degree, all of the light will be reflected. Hence, total internal reflection occurs as angle I is greater than C because angle of incidence is greater than the critical angle. When theta is equal to 45 degrees, the reflected light strikes side CD. Describe what happens when this reflected light strikes side CD. Now, side CD is this side. We have the exact same case here because as it strikes side CD, the angle of incidence is still 45. Because if you look at it here, uh, we know that according to the laws of reflection, the angle of incidence is equal to the angle of reflection. So this angle is also 45. And by math, two parallel lines, AP and DC, cut by a transversal. So the alternate angles are equal. So hence, angle of incidence here is also 45 degrees. Let me clean this diagram up. Basically, all we need to know is that this angle of incidence is also 45 degrees, which is more than the critical angle. Hence, total internal reflection will occur again. So we have to write that all, and all is important. All light will be reflected inwards. Next, question 6. A mobile phone network uses microwaves of frequency 1.9 into 10 to the power 9 hertz to transmit and receive signals. The speed of microwaves in air is 3 into 10 to the power 8 meter per second. Calculate the wavelength of these waves. So, wavelength into frequency is equal to speed of these microwaves. Hence, wavelength is equal to 3 into 10 to the power 10 to the power 8 divided by the frequency, which is 1.9 into 10 to the power 9 hertz. Hence, the wavelength is 0.16 meters. State two reasons why microwaves are used for mobile phone signals. Well, one is that they can pass through walls. So, of course, that's good. When people are inside their houses, they can talk and communicate on their phones. This is how it works. They can pass through walls. And the other is that only a small number of aerials or antennas is required. So, this is why microwaves are used. All mobile phone networks use digital signals to communicate with the phone. Describe with the aid of a diagram how a digital signal differs from an analog signal. So the diagram is simple enough. Now, a digital signal diagram will be like this. There's two fixed values, 1 and 0. And it's constantly either 0 or 1 because we can see these, it's not accurate, but roughly we can see these sharp spikes and dips because it's either 0, 1 here, 0, 1 here. Now, compared to an analog signal looks a bit like this. It's constantly varying. So that's what we can write. A digital signal is always one of either two values, whereas an analog signal constantly varies. State two advantages of using digital signals rather than analog signals. So we have two advantages that digital signals can be transmitted for longer distances since they can be regenerated. Because they can be manipulated by computers easily and thus like boosted, so travel longer. Also, digital signals can be directly, as I mentioned, used by computers, which analog can't, because computers, as you know, work with transistors and logic gates, which can either be on or off. So similarly, digital signals are either 0, which means the transistor is off, or 1, transistor is on. Number 7 shows a circuit that contains a battery, a switch, a voltmeter, and 340 ohm resistors. So the switch is open, and resistors R1 and R2 form a potential divider. Describe what is meant by a potential divider. Now, a potential divider basically divides the voltage of a circuit into two components, typically two resistors. So we can write it divides the potential difference or EMF or voltage, whatever you wish to write, into two different components based on the proportion of the resistances. So basically, the potential divider can't change the current in the circuit. As we know, current is equal to voltage by resistance. So since I is constant, what the while dividing the potential difference, as the as we know, voltage and resistance are directly proportional to maintain a constant current. So the more resistance one of the resistor has, the more potential difference is divided to it by the potential divider, as we'll see in the following questions. Next up, the question is the reading on the voltmeter is 7.5 volts. Calculate the EMF of the battery. Now, this is a bit tricky. So, this is the voltmeter we're talking about, and the reading on this voltmeter, which is connected to R1 only, is 7.5 volts. Now, as we can see, this forms a potential divider circuit. This one has a voltage of 7.5 volts. We know that all of these resistors are identical. So this resistor is equal to this. That means the voltage across this resistor is the same as the voltage across this resistor. So the voltage across this resistor, if you had a voltmeter, would also be 7.5 volt. So here, since the potential difference is divided between these two, it means the potential difference originally from the battery is the sum of these two, which is 15 volts. Now, the switch is closed. Calculate the resistance of the complete circuit. So if we close the switch, let's pretend the resistance of this circuit is the resistance of this plus the resistance of this system. The resistance of this system, since these two resistors are in parallel, we know, and both of them have a resistance of 40 ohms, we know that 1 by 40 plus 1 by 40 is equal to 1 by R. So that means 2 by 40 or 1 by 20 is equal to 1 by R. So R is equal to 20 ohms. So the resistance of this system is 20 ohms. And this resistor obviously is 40 ohms as given in the question. So the total resistance of the circuit is 40 plus 20, 60 ohms. Now calculate the reading on the voltmeter when the switch is closed. Now when the switch is closed, this system has 20 ohms of resistance and this system has 40 ohms of resistance. As we know, the EMF of the battery is 15 volts, which is going to be divided across these. So while the total resistance is 60 ohms, we know that R1 provides 2/3 of the resistance of the whole circuit. So as we discussed that voltage and resistance are divided proportionally, so that means 2/3 of the voltage also has to be given to R1. So that means 2 by 3 into the total EMF, which is 15 volts, which is 10 volts. This one will be given 5 volts since it has half the resistance of R1. That's why it's given 10 volts of potential difference. Question 8 mentions that electricity supplied to a town is transmitted using a high voltage cable. A transformer in the town has a soft iron core. Explain the principle of operation of a simple iron core transformer. So as we know, a transformer in this example, for example, is used to either decrease or increase the voltage of a power supply. Hence, how a transformer works with an iron core is it has a primary coil with an alternating voltage. The reason we need an alternating voltage is because, as we'll talk about later, to induce a current, you need a change in the magnetic field. And you need something to cut across a magnetic field. Since the transformer is stationary and not moving, if we have an unchanging voltage, a direct current, there's no change in magnetic field to induce a current. Since we have alternating current here and an alternating magnetic field is produced, there's a constant change in magnetic field which induces a current. So this magnetic field produced by the primary coil is transported by the iron core to the secondary coil. Now, due to the change in magnetic field, as we talked about, an induced EMF or electromotive force occurs in the secondary coil. The iron core is needed to transport this magnetic field. So an induced EMF occurs in the secondary coil. The magnitude or the amount of voltage produced depends on the number of turns in the secondary coil. The more the turns, the more the EMF. Because as we know, the ratio of number of turns to voltage is directly proportional in a transformer. The transformer steps up the supply voltage down from 220,000 volts to 33,000 volts. There are 450 turns on the secondary coil. Calculate the number of turns on the primary coil. So as we were talking about, and just as a mention, the more the turns, the more the voltage, because then there's more lines of wire to cut across the field, so a greater induced EMF. So as we know, the number of coils on primary coil by number of turns on secondary coil is equal to voltage in primary coil by voltage in secondary coil. So using this formula, we have x, let's just take the number of turns on the primary coil as x by 450 is equal to 20,000 by 33,000. So if we just solve this simple equation, we have 220,000 into 450 by 33,000, which is 3,000 turns. Next up, we have the electrical power transfer to the transformer by the high voltage cable is 77 megavolts. Calculate the current in the primary coil. So, as we were talking about last question, current is equal to power by voltage. P is equal to IV. So, the power as we have been given in the question is 77 million watts. And the voltage, here we are talking about the electrical power transferred to the transformer. So this is the primary coil. So the voltage in the primary coil is 220,000 volts. Hence, if we do basic math, some cancelling, we have 7700 by 22. 350 amperes is the current in the primary coil. Now, question 9, we have this figure that represents all the particles in a neutral atom of a radioactive isotope X1. Determine the number of neutrons in this atom and explain how the answer is obtained. So, we have the fact that this is a neutral atom, which means that the number of electrons is equal to the number of protons. We can count 5 electrons at the side at the in the orbits of this atom. So we can see that here in the nucleus there are 5 white circles. So these must be the protons. That means the neutrons are these gray circles, which if you count are 7. And the explanation we'll write 12 particles in the nucleus. We know number of electrons equal to number of protons, which is 5. So it's 12 minus 5 equal to 7. Now, the isotope X1 is a beta emitter that decays to the stable isotope X2. Describe how a nucleus of X2 differs from a nucleus of X1. Now, the nucleus of X2, so we know that during beta emission by isotope X1, a neutron in the nucleus will split into one electron and a proton. So that means how this will differ is it'll have one extra proton and it'll have one less neutron, which is the neutron which decayed. And we won't have to mention about the electrons since it says how the nucleuses differ and electrons are outside the nucleus. Now, it suggests why isotope X2 is stable whereas X1 is not stable. We can say that since X2 has less number of neutrons, its nucleus is less heavy, which is why it's more stable. So we can just write that X2 has less excess uh, neutrons. The excess is not mandatory, but it just adds emphasis to the decay situation. So since it has lesser neutrons or fewer neutrons than X1, it's more stable. Now, question C asks that the half-life of X1 is approximately 20 milliseconds. Define the term half-life. Now, the term half-life is basically the time required for a radioactive isotope's rate of decay to half. That's basically it. So yeah. Now, next question is suggest one reason why isotopes with very short half-lives are especially hazardous. So if an isotope has a very short half-life, that means the time taken for decay is really low. That means the rate of decay is high. So that is the reason, since the rate of decay is very high, that means the number of particles emitted per second is really high. That's why they are hazardous, because more alpha or beta particles or gamma rays are released per second, so that's more dangerous to us. So we've got the last question, number 10. Pluto is a dwarf planet. Figure 10.1 shows the direction of motion of Pluto as it follows its elliptical orbit around the sun. Point X is the point in the orbit closest to the sun, and point Y is the point furthest away. The orbital speed of Pluto varies as it orbits the sun. Describe how the speed of Pluto varies as it moves from X to Y, then back to X. Now, this is space. So there's no atmosphere, no air resistance. So there's no other drag force or anything. So we're just dealing with the energy of Pluto itself. So its internal energy is made up of two things: gravitational potential energy and kinetic energy. Its gravitational potential energy is basically like uh, here the reference point is the sun, which is exerting a gravitational pull towards it. So the further it is from the sun at point Y, the greater its gravitational potential energy. Similar to how in normal experiments, the greater the height, the more the gravitational potential energy, because we're on Earth. Here that it's far from the sun. The sun exerts the gravitational pull. So the distance from the sun, the more the distance, the more the gravitational potential energy. So since we know that the internal energy is made up of gravitational potential and kinetic energy, here as its gravitational energy is maximum, its kinetic energy is minimum. So at y, the speed is basically zero. Now as we move to x, since we know that at x, it's the point closest to the sun, hence distance from the sun is least. So gravitational potential energy is minimum, hence the kinetic energy will be maximum because there's no energy loss, there's no air resistance. Whatever the gravitational potential energy, it's transferred into the kinetic energy. So as it moves from x to y, it's practically losing kinetic energy and it's being converted to GPE, gravitational potential energy. Hence, as it moves from x to y, we can write that its speed decreases since kinetic energy decreases, and kinetic energy is basically proportional to speed. Speed decreases at first, then speed increases from y to x because here GP is maximum, here K is maximum. So here all the gravitational potential energy gets transferred to kinetic energy, which increases the speed. Now, explain in terms of energy transfers why the speed of Pluto varies this way. I have already done that. So we've basically got to write what I just explained. Closest to the sun at x, GPE is minimum, KE is maximum. At y, GPE max and KE minimum. So all the kinetic energy, so the kinetic energy plus the gravitational potential energy is constant. So as they move, the kinetic energy is transferred to the gravitational potential energy, and gravitational potential energy transferred to kinetic energy, and vice versa, depending on the scenario. So we can write that this is why the speed of Pluto varies, because x to y, Ke transferred to GPE, and y to x, GPE is transferred to Ke, kinetic energy. Then the average temperature on the surface of Pluto is 43 Kelvin. Convert this temperature to a value in degrees Celsius. We know that to convert from Kelvin to Celsius, we have to subtract 273. So here, 43 minus 273 is minus 230 degrees Celsius. So now the last subpart we have is Pluto has a white surface as shown in figure 10.2. As Pluto rotates, the white surface alternately faces towards and away from the sun. Explain how this affects the temperature of Pluto as it rotates on its own axis. So here we have to use the properties of thermal physics. As we know that white surfaces are good reflectors of thermal energy and black surfaces are good absorbers. So we write this here and then we mention that when the white surface is exposed to the sun, that means it doesn't heat up that well. Since we know that most of the energy will be reflected. Whereas when the black surface is towards the sun, there'll be a significant temperature increase as it absorbs thermal energy well. So, yeah, that's it for this paper. All of the questions are done. I hope you all enjoyed and understood what I said. So, yeah, that's all for my side.
That wraps up today's episode. We hope you found it helpful and feel more confident about tackling the papers. We've got plenty more episodes coming your way, so don't forget to subscribe and hit the notification bell to stay updated. Thanks for watching, and we'll see you in the next episode.